Welcome to this lecture on vibration and noise control. Today we are diving into the third part of the Unit 3, focusing crucial concepts of eigenvalues and eigenvectors. In the realm of vibration analysis, understanding the natural modes of vibrations is very much essential. These modes represents the characteristic ways a system oscillates when disturbed. Let's visualize these first three modes for a specific system. Here we see the first mode. Notice how the system deflects in a simple single curve. The point marks for x1, x2, x3 represent relative amplitude of vibration at different location in its first mode. Now observe the second mode. In this mode, the system vibrates with a more complex shape, exhibiting a node, a point of zero displacement. Amplitude at different locations are indicated by x. Finally, we can look the third mode. This mode displays an even more intricate vibration pattern with two nodes. The corresponding amplitudes are labeled as x1, x2 and x3. These mode shapes and their associated frequencies or eigenvalues are fundamental to predicting and controlling vibrational behavior of any mechanical systems. Understanding these concepts allows engineers to design structures and machines that operate safely and efficiently, minimizing unwanted noises and vibrations. This lecture is brought to you by Dr. C. Sendamarikannan, Associate Professor in the Department of Mechanical Engineering at SVC. We are looking at the formulation of eigenvalue problems, which is fundamental in vibration analysis. The eigenvalue problem is expressed as lambda with this is independent matrix minus mass matrix X, where lambda is equal to 1 by omega square, where this K represents the stiffness matrix, M represents mass matrix, X is the eigenvector representing the mode shape, and this O vector is the zero vector. The term omega represents the natural frequency. By multiplying the equation by the inverse of the stiffness, we can rewrite this equation as lambda into identity matrix, which can also be expressed as in this way, and it is defined as in the form of D, that is dynamic matrix, which is equal to the product of the inverse of the stiffness matrix and product matrix that is given here. So D dynamic matrix is equal to K inverse into mass. For non-trivial solution for X eigenvector, the characteristic determinant must be equal to 0. This is given by the equation. Finally, it is important to note that when dealing with systems that have a large number of degree of freedom, numerical methods are typically employed to solve these eigenvalue problems. We are presented with a system consisting of three masses, mass 1, mass 2, mass 3, connected by springs with each spring constant K1, K2, K3. Masses are shown on rollers, allowing them to move horizontally. External forces F1 of t, F2 of t, F3 of t can act on each mass, resulting in displacement respectively as x1, x2, x3. Our goal is to determine the natural frequencies and mode shape of this particular system under the condition that all spring constants are equal, that is K1 equal to K2 equal to K3 equal to K, and all masses are equal, that is M1 equal to M3 equal to M. The natural frequencies represent the frequencies at which the system will naturally oscillate when disturbed, and the mode shape describes the relative motion of the masses at each natural frequencies. We are now looking at the solution for finding the natural frequencies of 3 degree of freedom. First step is involving determining the dynamic matrix denoted as D. This matrix can be expressed as the product of inverse of the stiffness matrix and mass matrix. It can also be represented using flexibility matrix, since inverse matrix of stiffness is nothing but flexibility matrix A. Flexibility matrix A for the system is given by 1 by stiffness multiplied by the matrices of 111, 122, 123. The mass matrix for the system is given by mass multiplied by the identity matrix. Hence it is, there is only one mass 1 at M1, mass 2 at M2, mass 3 at M3, other things and all 0. So it is 100, 010, 001. Therefore, the dynamical matrix is obtained by multiplying the flexibility matrix and mass matrix using the mass matrix multiplication and with the flexibility matrix. What results is, it is equivalent to m by k of this arrangement of matrices. This dynamic matrix will then be used to solve for the natural frequencies of the 3 degree of freedom system. I request your sincere attention in this problem because in this video I am explaining one typical example of how to identifying the eigenvalue eigenvector. In the next videos I will solve the remaining problems, but this is the basic explanation of how to identify eigenvalues and eigenvectors for a 3 degree of freedom systems. Let we go. Continuing our analysis of the 3 degree of freedom systems, we now focus on deriving the frequency equation. Frequency equation is obtained by setting the determinant of the matrix equal to 0. Here lambda is the related to the natural frequency omega by the equation lambda equal to 1 by omega square. D is the dynamic matrix we derived earlier. Substituting these values, we get the determinant of this following matrix should to be equal to 0. To simplify further, we divide the entire determinant equation by lambda cube. Then we introduce a new variable alpha that is then equivalent to m divided by k alpha. Substituting this into the determinant equation and expanding it. Okay, expanding it. And also we are substituting alpha equal to m by k lambda. We are arriving the following cubic equation in terms of alpha itself. The root of this cubic equation will give us the values of alpha, which can then determine the natural frequencies of this 3 degree of freedom systems. We now have the solution to the cubic equation for alpha, which is yielded 3 roots. Alpha 1 equal to 0.19806, alpha 2 equal to 0.1553, alpha 3 equal to 3.2470. Using the relationship alpha equal to m omega square by k, we can find the corresponding natural frequencies, that is omega equal to 0.444504 to the root of k by m. The similar fashion omega 1, omega 2, omega 3 is calculated. These are the 3 natural frequencies of the 3 degree of freedom systems. Once we determine these natural frequencies, next step is to calculate corresponding eigenvectors which represents mode shapes of the system. This can be done by substituting the value of lambda equal to 1 by omega square for each natural frequencies and solving for the eigenvector x1, x2, x3 matrix in transpose form. It is written in transpose form. This process will give us 3 distinct mode shapes, one for each natural frequencies. We now proceed to calculate the first mode shape of the system. To do this, we substitute the eigenvalue lambda 1 equal to 5.0489 into the characteristic equation in this equation. Remember that in our case, this lambda I minus d took this form. Since if you are substituting this value and solving up to this, what we will get means the matrix will be resolved into this way, then which simplified like this. This matrix equation represents a system of three linear homogeneous equations with three unknowns x1, x2, x3, which are the components of the first mode eigenvector. Since alpha 1, that is lambda 1, is an eigenvalue, the determinant of the coefficient matrix is 0, meaning the equations are not independent. Therefore, we can express any two of the unknowns in terms of remaining one, allowing us to define the first mode shapes. To find the first mode shape, we use the system of equations derived in the previous step. Let's take the first two equations, that is x1 plus x2, that is which can be rearranged in such a way to get this equation, that is x2 plus x3 equal to 4.0489 x1. From the matrix only it has been rearranged. Similarly, this equation also rearranged. Solving these two equations, we can able to get what is x2 in terms of x1, x3 in terms of x1. By assuming or choosing x1 arbitrarily as 1, substitute 1 here, then x2 will be equal to 1.089, then x3 equal to 2.2470. So if I am writing the x1, x2, x3 in matrix form, we will get 1.8019, 2.2470. If for a scale in x-axis, if I take the length of the beam, for example, at the mass exactly at mass 1, what is the unit displacement? I will take the scale as 1 centimeter equal to 1 unit. I can draw 1 centimeter here. The second mass I can able to draw 1.8 centimeter. The third mass I can able to draw 2.24 centimeters. So this implies deflection of this system at the third mass is 2.24, second mass is 1.8, first mass is 1. This corresponds to first mode of the system, first mode vibration. That is for the first natural frequency, the mode of vibration will be look like this. Next, we will in the next slides we solve for second mode of vibration and third mode of vibration. Now we will calculate the second mode shape. The same equation, we substitute the lambda 2 value 0.6430 into this characteristic equation. Again we get the simplified form. Afterwards we will get this lambda matrix. Okay, so in that, once again what we have to do, we have to substitute x1 equal to 1 or else x2 equal to, here in this case it is lambda 2, so we substitute x2 equal to 1 and we find the other mode things. Let me do it in the next slide. To determine the second mode shape, we use the system of equations obtained by substituting the second eigenvalue. Let's consider this first two equations. Solving by rearranging them, we can able to got the solution of x2 in terms of x1, x3 in terms of x1 once again. So in that case, once again for the second mode shape, x1 is chosen arbitrarily. So in this case also we are choosing x1 as 1 because this is the one we have to assume the value. If x1 is 1 unit, x2 will be 0.4450. Similarly, x1 is 1 unit, then x3 will be equal to minus 0.8020. So for these values, to determine and draw the second mode shape, what I am going to do, I am drawing in the x-axis the length of the system, y-axis is corresponding to amplitudes x1, x2, x3. So exactly at mass 1, I want to use x1 equal to 1. So take a scale draw 1 centimeter line here. Okay, then this will be 1 centimeter. If this is 1 centimeter, x2 will be 0.4450. So at exactly mass 2, you draw a line with 0.4450. Then at x3 we have to draw at mass 3 we have to draw it, but this value is negative, hence minus 0.8020 we have to draw below the xy line. Now if we connect these three dots, we will get the second mode shape, and very important thing is we got the first, there is a node. What is node? Node is nothing but there is no vibration. So we got a, in the first scenario, in the first mode shape, there is no nodes at all. The second mode shape, we will get one node. So this vector represents this second mode shapes, and accompanying this diagram illustrates the relative displacement of these three masses when the system vibrates in the second mode. Let we calculate the third mode in the next slide. Finally, let's calculate the third mode shape. We substitute the third eigen value, that is lambda 3.3078, into the characteristic equation, and simplifying it further, we got this matrix multiplied by x1, x2, x3 vector, which is then equal to 0. So from this we can able to get the equation. Okay, so that the first equation what we can get is 0.6922 x1 equal to this x2 and x3, which is then the second equation is we can able to get from this. So by assuming x1 equal to 1, once again what we will get, x2 equal to 1.2468 in minus, x3 will be 0.5544. Now it is positive. The same version for the first mode, second mode, what I described. Here also you take a pen and pencil and also scale. You draw a line x-axis. This is representing the mass positions, and this y-axis represents the amplitude. At mass position, first mass position you draw, since we assumed x1 equal to 1 centimeter line. In the mass position 2, you draw minus 1.2468, that is below this line. This, since it is negative, draw a line of 1.2468 centimeter. Then at the third mass position you can draw a line of 0.5544 centimeter. So now you connect these dots, then what you get is a beautiful mode shape, which is representing the third mode shape, which is an intricate complex mode shape, which is having two nodal points. What is nodal points? Node points is nothing but the point at which no vibration will occur. This slide concludes the solution to the problem of finding natural frequencies and mode shapes of the given 3 degree of freedom systems. We have successfully determined 3 natural frequencies and their corresponding mode shapes. Let's examine these modes and understand their significance. First mode represents the system vibrating at its lowest natural frequency. As we see in the illustration, when the system oscillates in this mode, all 3 masses move in the same direction. If we set the amplitude of the first mass to unity, second mass vibrate with a larger amplitude than first mass, that is approximately 1.8 times that of the first, and the third mass vibrates with largest amplitude, approximately it is 2.25 times that of the first. This is the fundamental mode of vibration. The second mode occurs at the second natural frequency. In this mode, masses vibrate with a more complex pattern. First and second masses move in the same direction, that is the positive direction, with the second mass having a smaller amplitude, approximately 0.445 times that of the first. The third mass moves in the opposite direction, an amplitude of about 0.8 times of the first. This mode exhibits one node, a point of zero relative displacement between the masses. Third mode corresponds to the highest natural frequency of the system. Here the vibration pattern is even more intricate. First mass moves in one direction, second mass moves in opposite direction with an amplitude of 1.25 times that of the first, and the third mass moves in the original direction again with an amplitude of about 0.55 times that of the first. This mode exhibits two nodes. Understanding these natural frequencies and mode shapes is crucial in engineering design. It allows us to predict how a system will respond to external forces or disturbances. By knowing the natural frequencies, we can design systems to avoid resonance, a phenomena that occurs when the excitation frequency matches a natural frequency, leading to potentially a damaging large amplitude of vibrations. The mode shapes, on the other hand, helps us to understand the relative motion of different parts of the system during the vibration, which is essential for designing effective vibration control measures. In essence, this analysis provides a complete understanding of the system's inherent dynamic characteristics. We now delve into an important property of normal modes called orthogonality. This property provides a powerful tool for analyzing and understanding the behavior of vibrating systems, especially those with multiple degrees of freedom. Let's recall the fundamental equation of motion for free vibration of system, that is stiffness matrix minus omega square multiplied with mass matrix determinant of displacement vector equal to 0. For each natural frequency and its corresponding mode shape, this equation holds true. So far, the ith natural frequency omega and its mode shape vector x of I satisfy it such that we having the relationship omega I square mass matrix into x vector at I equal to stiffness matrix into x vector at I. The principle of orthogonality states that the modes of vibrating system are orthogonal with respect to mass and stiffness matrices. What does this mean? It means if we take ith mode shape, multiply it by the mass matrix, and jth mode shape, we have I and j are different, the result is 0. Mathematically, we are expressing it in the form of, that is, similar the mode shapes are orthogonal with respect to the stiffness matrix. This orthogonality property is incredibly useful. For instance, when analyzing the response of a multi-degree of freedom system to external forces, we can often express the system's motion as a linear combination of its normal modes. Due to orthogonality, the equations of motions for each mode become independent of each other. This significantly simplifies the analysis, allowing us to treat each mode as a single degree of freedom system and then combine the responses to find the overall system response. In essence, the orthogonality of normal modes provides a way to decouple the complex vibrations of a multi-degree of freedom system into a set of simpler independent modal vibrations, making the analysis and understanding of the systems much more manageable. In our discussion of the orthogonality of normal modes, which touched upon relationship between mode shapes, mass and stiffness matrix, now let's explore what happens when we normalize these mode shapes. Normalization is a process where we scale the mode shape vectors in a specific way. One common method is to normalize with respect to the mass matrix, such that the generalized mass for each mode becomes unity. The generalized mass for the ith mode is given by the vector x of phi. If we choose a scaling factor for each mode shapes such that it is equal to 1, we say the modes are mass normalists. When mode shapes are normalized in this manner, an interesting specific simplification occurs within the generalized stiffness matrix. Due to the orthogonality properties we discussed earlier, when we form a matrix using mass normalized mode shapes and then compute the product, we will get the model matrix resulting generalized stiffness matrix, which will become as a diagonal matrix. The diagonal elements of the matrix are the squares of the natural frequencies of the system, omega 1 square, omega 2 square, and so on up to omega n square, where n is degree of freedom of systems. This diagonalization of the generalized stiffness matrix through mass normalization is a powerful result. This further emphasizes the independence of the normal modes. In essence, by appropriately scaling our mode shapes, we can represent the system's stiffness property in a very straightforward manner, directly linked to the system's natural frequencies. This simplification is highly beneficial in advanced vibration analysis and control applications. Thank you for engaging in this detailed discussion on the analysis of a 3 degree of freedom vibration systems. We begin by understanding fundamental concept of eigenvalues and eigenvectors in the context of vibration and noise control. We then formulated the eigenvalue problem mathematically, which led us to analyze a specific system with 3 masses and 3 springs. Through a step-by-step process, we derived the frequency equation for this system and subsequently found its 3 natural frequencies. Following this, we meticulously calculated corresponding 3 mode shapes which describe characteristic pattern of vibration for each natural frequency. We also explored the important property of orthogonality of normal modes and how normalizing these modes simplifies the representation of systems mass and stiffness properties. Understanding, once again I am emphasizing that understanding natural frequencies and mode shapes is crucial for predicting and controlling the vibrational behavior of mechanical systems, ensuring the safe and efficient operation. Thank you for your time and attention.